Turn off the lights, my friend. I am HyperSleep Logs. Together, we're stepping into the deep mysteries of the cosmos. Our journey begins, right now, when we looked too far, the James Webb Space Telescope and the unraveling of everything we thought we knew. Let me tell you about the moment everything changed. It wasn't dramatic, at least not in the way you might expect. There were no explosions, no alarm bells, no scientists running through hallways screaming. It was quieter than that. More insidious. It was the slow, creeping realization that something was very, very wrong. I'm talking about the James Webb Space Telescope, of course. That magnificent, $10 billion machine we launched into space with such high hopes and grand expectations. We built it to answer the biggest questions humanity has ever asked. How did the universe begin? What did the first stars look like? How did galaxies form? When did it all start? We thought we knew the answers, or at least we thought we were close. We had the Big Bang Theory, which had been tested and refined over nearly a century. We had computer simulations that could model the evolution of the entire universe from microseconds after its birth to the present day. We had a timeline, a story, a narrative that made sense. And then Webb opened its golden eyes and showed us we were wrong. Not slightly wrong. Not off by a little bit. Fundamentally, profoundly, cosmically wrong. The images started coming back in July 2022, and at first, everyone was just in awe of their beauty. And they are beautiful, make no mistake. The clarity, the resolution, the sheer depth of field, it's like nothing we've ever seen before. We were looking further back in time than any human had ever looked. We were seeing the universe as it was when it was just a baby, a few 100 million years old. But here's the thing, babies aren't supposed to look like that. Let me explain what I mean. According to our models that had been tested and verified for decades, the early universe should have been pretty simple. After the Big Bang, it took time for things to get organized. Gravity had to pull matter together. The first stars had to form, live out their lives, explode, and scatter heavy elements into space. Then those elements had to coalesce into new stars, new planets, new galaxies. It was supposed to be a gradual process, taking hundreds of millions, even billions of years. The first galaxies we expected to see should have been small, messy, irregular. Think of them as cosmic toddlers, stumbling around, not quite sure how to walk yet. Small clumps of stars, chaotic and disorganized, gradually figuring out how to be proper galaxies. That's not what Webb found. Instead, it found monsters. Massive, mature, beautifully structured galaxies that looked like they belonged in the modern universe, not in its infancy. Galaxies as large as our own Milky Way, existing just 300 to 500 million years after the Big Bang. Galaxies with spiral arms, with organized structures, with populations of stars that suggested multiple generations had already lived and died. To give you a sense of scale here, if the universe were a human life, these galaxies would be like finding a fully grown adult at the age of 2. It doesn't make sense. There simply wasn't enough time. And it's not just one galaxy. It's not an anomaly we can explain away as a fluke. It's dozens of them. Hundreds, maybe. The more we look, the more we find. They're everywhere in the early universe, these impossible galaxies that shouldn't exist. I remember when the first papers started coming out, tentatively suggesting that maybe, just maybe, our timeline was off. The titles were cautious, hedged with caveats and question marks. But you could feel the undercurrent of anxiety. Because if these galaxies are real, if they're not some instrumental artifact or some weird trick of the light, then we have a serious problem. We have to explain how you build a galaxy that fast. And right now, we can't. Think about what it takes to make a galaxy. You need stars, obviously. Lots of them. Billions of them. And stars take time to form. They start as clouds of gas that collapse under their own gravity. As they collapse, they heat up, and eventually, if they get hot enough, nuclear fusion ignites in their cores. They start burning hydrogen into helium, producing the light and heat that makes them stars. But that's just the beginning. The first stars in the universe were made of simple stuff, just hydrogen and helium, the elements created in the Big Bang itself. They didn't have heavy elements like carbon, oxygen, iron. Those elements didn't exist yet. They had to be created inside the cores of stars, forged by nuclear fusion at incredible temperatures and pressures. And here's the kicker, those heavy elements only get released into space when stars die. When a massive star runs out of fuel, it explodes in a supernova, scattering its guts across the cosmos. Only then can the next generation of stars form, this time enriched with heavy elements. This is a process that takes time. A lot of time. The first stars had to form, live their lives, die, and scatter their elements. Then the second generation had to form. And possibly a third generation, depending on how enriched you want your galaxy to be. In our models, this takes at least 1 billion years, maybe more. But these galaxies exist when the universe was only 300 to 500 million years old. The math doesn't work. The timeline doesn't fit. It's like the universe hit the fast forward button, and we don't know why. Now, I know what you're thinking. Maybe our models are just a bit off. Maybe stars formed faster than we thought, or maybe the first galaxies were more efficient at pulling matter together. Maybe we just need to tweak a few parameters, but just a few assumptions, and everything will be fine. And yes, that's what a lot of scientists are trying to do. They're working overtime, running new simulations, testing new hypotheses, trying to find a way to make the data fit the theory. But here's the uncomfortable truth, the more they try to fix it, the more problems they find. Because it's not just the galaxies. It's everything. Remember the Hubble constant. It's the number that tells us how fast the universe is expanding. It's one of the most important numbers in all of cosmology, because it tells us the age of the universe, its size, its ultimate fate. We have two main ways to measure it. One method looks at the cosmic microwave background, the afterglow of the Big Bang, the faint radiation left over from when the universe was just 380,000 years old. By analyzing the patterns in this radiation, we can calculate how fast the universe was expanding back then, and extrapolate to the present day. The other method looks at nearby stars called Cepheid variables. These are special stars that pulse with a regular rhythm, and the period of their pulsing tells us how bright they actually are. By comparing their actual brightness to how bright they appear from Earth, we can calculate their distance. And by measuring how fast they're moving away from us, we can calculate the expansion rate of the universe. Both methods are solid. Both have been tested extensively. And both give you a number for the Hubble constant. The problem? They don't give you the same number. Not even close. The cosmic microwave background method gives you about 67 kilometers per second per megaparsec. The Cepheid method gives you about 73. That might not sound like a huge difference, but in science, especially in cosmology, it's enormous. It's a gap that's too big to explain by measurement error or statistical fluctuation. We call this the Hubble Tension, and it's been bothering cosmologists for years. At first, people thought it would go away as our measurements got more precise. Better telescopes, better instruments, better analysis techniques, surely the two numbers would converge. They didn't. If anything, the gap got wider. And this is where the James Webb Space Telescope was supposed to come to the rescue. Webb was supposed to measure distances with unprecedented precision, to nail down the Hubble constant once and for all, to be the tiebreaker that would settle the debate. Instead, it made things worse. Webb confirmed the Cepheid measurements with stunning accuracy. The number is 73, give or take a tiny margin of error. There's no wiggle room anymore. No possibility that the measurements were off. The Hubble tension is real. Which means something is deeply wrong with our understanding of the universe. Either our model of the cosmic microwave background is wrong, which would mean our understanding of the early universe is wrong, or the expansion rate has changed in ways we didn't predict, which would mean our understanding of dark energy is wrong. Or both. Or something even weirder that we haven't thought of yet. This is what keeps cosmologists up at night. This is the crisis that's shaking the foundations of the field. Because if we can't even get the expansion rate right, what else are we missing? Let me take you deeper into this, because I think it's important to understand just how fundamental this problem is. Our entire cosmological model, the thing we call the lambda CDM model, which stands for lambda cold dark matter, is built on a few basic assumptions. One of those assumptions is that the universe is homogeneous and isotropic, meaning it looks basically the same in all directions and at all locations. Another is that general relativity, Einstein's theory of gravity, accurately describes how matter and energy interact on cosmic scales. But what if those assumptions are wrong? What if the universe isn't as uniform as we think? What if there are large-scale structures or flows that we're not accounting for? What if gravity works differently on the scale of billions of light years than it does in our solar system? These are radical ideas. They would require us to throw out or fundamentally revise theories that have been the bedrock of physics for a century. Nobody wants to do that lightly. But the data is forcing our hand. And then there are the black holes. Oh God, the black holes. At the centers of most large galaxies, including our own Milky Way, there's a supermassive black hole. These are monsters, millions or billions of times the mass of our Sun. They're thought to play a crucial role in galaxy formation and evolution, regulating star formation, shaping the structure of the galaxy. In our models, these black holes grow slowly over time. They start as smaller black holes, maybe a few dozen or a few hundred times the mass of the Sun, formed from the deaths of the first massive stars. Then they gradually accumulate mass by consuming gas and dust and occasionally merging with other black holes. It's a slow process, taking billions of years. But when Webb looked at those ancient, impossible galaxies, it found supermassive black holes that were already fully grown. Black holes with masses of millions or even billions of solar masses, existing when the universe was less than 1 billion years old. Again, there simply wasn't enough time. A black hole can only grow so fast. There are physical limits to how quickly it can consume matter. If you try to feed it too fast, the infalling material heats up and radiates so much energy that it actually pushes more material away, limiting the growth rate. This is called the Eddington limit, and it's a hard constraint. You can't violate it without violating the laws of physics as we know them. So how did these supermassive black holes get so big so fast? Some scientists are proposing the existence of direct collapse black holes that form not from the death of a star, but from the collapse of an entire massive cloud of gas. These could start out much bigger, maybe thousands or tens of thousands of solar masses, giving them a head start on growth. Others are suggesting that maybe the Eddington limit can be exceeded under certain special conditions in the early universe. Maybe the gas was denser, or the magnetic fields were different, or some other factor allowed black holes to grow faster than we thought possible. And then there's the really wild idea, dark stars. This is one of my favorite hypotheses, not because I think it's necessarily right, but because it's such a beautiful example of how scientists think when they're backed into a corner. The idea is this: in the very early universe, before the first normal stars formed, there could have been massive objects powered not by nuclear fusion, but by the annihilation of dark matter particles. These dark stars would have been enormous, hundreds or thousands of times the mass of the Sun, and incredibly luminous. More importantly, they would have been short-lived. They would burn bright and fast, then collapse directly into massive black holes, seeding the centers of galaxies. If dark stars are real, it would solve multiple problems at once. It would explain the supermassive black holes. It would explain why the early universe seems so bright and active in Webb's images. And it would finally give us some direct evidence for dark matter, which, despite making up 27% of the universe, we've never actually detected. But it's still just a hypothesis. A beautiful, elegant hypothesis that fits the data, but one that requires us to accept the existence of objects we've never seen and physics we don't fully understand. Which, at this point, seems to be par for the course. Let me step back for a moment and talk about dark matter and dark energy, because they're central to this whole crisis, and I think a lot of people don't fully appreciate how weird the situation is. Here's the thing, everything you can see, every star, every planet, every galaxy, every atom in your body, makes up only about 5% of the universe. 5%. That's it. The other 95% is invisible to us. About 27% is dark matter, which we know exists because we can see its gravitational effects. Galaxies rotate too fast, clusters of galaxies hold together too tightly, light bends around invisible mass. Something is out there, something with mass and gravity, but it doesn't emit, absorb, or reflect any light. We call it dark matter because we literally cannot see it. And about 68% is dark energy, which is even weirder. Dark energy is whatever is causing the expansion of the universe to accelerate. Not just expand, but accelerate, getting faster and faster over time. We have no idea what it is. It's not matter, it's not radiation, it's something. Something that has a repulsive effect on the fabric of space itself. Think about that for a second. We've built this incredibly sophisticated model of the universe, tested it with observations, refined it over decades, and it works remarkably well. It can explain the cosmic microwave background, the large-scale structure of galaxies, the abundance of elements, all sorts of things. But it only works if we assume that 95% of the universe is made of stuff we've never detected, don't understand, and can't explain. That's not great, right? I mean, imagine if you had a theory of how cars work, and it accurately predicted the behavior of cars in all sorts of situations, but only if you assumed that 95% of every car was made of invisible, undetectable magic. You'd be pretty skeptical of that theory, wouldn't you? And yet, that's where we are with cosmology. Because the alternative, that our entire model is wrong, is even more terrifying. But now, with Webb showing us impossible galaxies and confirming the Hubble tension, we're being forced to confront the possibility that maybe, just maybe, we've been fooling ourselves. Maybe dark matter and dark energy aren't real physical things, but rather symptoms of a deeper problem with our theories. Maybe gravity works differently on cosmic scales than we think. Maybe Einstein's general relativity, as brilliant as it is just an approximation that breaks down when you apply it to the entire universe. This idea is called modified Newtonian dynamics, or MOND, and its more sophisticated relatives like modified gravity theories. The basic idea is that instead of inventing dark matter to explain why galaxies behave the way they do, we modify the laws of gravity themselves. For a long time, MOND was considered a fringe idea, relegated to the margins of physics. The mainstream view was that dark matter was real, we just hadn't detected it yet, and any day now, experiments deep underground would catch a dark matter particle colliding with normal matter. But those experiments have been running for decades, and they haven't found anything. And now Webb is showing us a universe that doesn't match our dark matter models. So maybe it's time to take modified gravity more seriously. Or maybe, and this is the idea that really messes with my head, maybe we're asking the wrong questions entirely. What if the Big Bang wasn't the beginning? I know. The Big Bang is the cornerstone of modern cosmology. It's the moment when everything began, when the universe exploded into existence from a single point of infinite density and infinite temperature. It's been confirmed by multiple lines of evidence: the expansion of the universe, the cosmic microwave background, the abundance of light elements. But what if it wasn't a beginning, but a transition? This is the idea behind the Big Bounce theory, and it's gaining traction as Webb's observations pile up. The concept is elegant in its simplicity. Instead of the universe beginning with a bang, it's just one phase in an eternal cycle of expansion and contraction. The universe expands for trillions of years, eventually stops, and then starts contracting, falling back in on itself. All the matter and energy collapse down to a tiny volume, and then, instead of forming a singularity, which is what the equations predict, something happens. Quantum effects kick in, or some new physics we don't understand, and the collapse reverses. The universe bounces, expanding again into a new cycle. If this is true, then the impossible galaxies aren't impossible at all. They're survivors. Remnants from the previous cycle, carried through the bounce into our current universe. This would explain why they look so mature. They didn't just form 300 million years after our Big Bang. They might be billions or trillions of years old, formed in a previous universe. It would explain the heavy elements. Those aren't from the first generation of stars in our universe. They're from countless generations in the universe before. It would explain the supermassive black holes. They didn't grow fast, they're just really old. It's a radical idea, for sure. It requires us to imagine that the Big Bang, this pivotal moment we built our entire cosmology around, wasn't a moment of creation, but just a moment of transition. One beat in an infinite cosmic rhythm. But radical times call for radical ideas. And these are radical times. Now, I should be clear, not all scientists are ready to abandon the Big Bang or embrace the Big Bounce. Far from it. The Big Bang theory has been incredibly successful, and it would take extraordinary evidence to overturn it completely. So what are the more conservative approaches? What are scientists who want to save the Big Bang model proposing? One of the leading ideas is called early dark energy. The concept is that in the first moments after the Big Bang, there was a temporary burst of dark energy that accelerated the expansion of the universe much faster than we thought. This would have allowed matter to clump together more quickly, speeding up the formation of stars and galaxies. Think of it like a turbo boost for gravity. For a brief period, maybe just a few 100 million years, the universe was expanding rapidly. But at the same time, the conditions were perfect for structure formation. Matter could fall together faster, stars could form more efficiently, and galaxies could mature more quickly. It's an elegant solution, and it might explain a lot of what we're seeing. But it's also ad hoc. We're essentially inventing new physics to patch a hole in our theory. And while that's not necessarily wrong, sometimes nature really is more complex than our models. It does make you wonder if we're just kicking the can down the road. Because here's the thing, if we need early dark energy to explain the first galaxies, what else might we be missing? What other aspects of the universe might require new physics that we haven't thought of yet? It's a slippery slope. Once you start adding free parameters and new components to your model, it can become increasingly difficult to test. You can always adjust the model to fit new data, but at some point, you have to ask if you're actually explaining anything or just creating a more elaborate story. This is the danger of epicycles, a reference to the old geocentric model of the solar system, where astronomers kept adding circles upon circles to explain the motion of the planets, refusing to accept the simpler explanation that Earth wasn't at the center. Are we doing the same thing with cosmology? Are we adding dark matter and dark energy and early dark energy and modified this and tweaked that, all to avoid confronting the possibility that our fundamental model is wrong? I don't know. I genuinely don't know. And neither does anyone else, which is kind of the point. We're in uncharted territory here. We're watching a major scientific paradigm come under stress, and we don't know if it's going to adapt and survive, or if it's going to collapse and be replaced by something new. This is both terrifying and exhilarating. Terrifying because uncertainty is uncomfortable, especially when it comes to something as fundamental as our understanding of the universe. But exhilarating because these are the moments when real breakthroughs happen. When the old certainties crumble, new ideas can take root. Let me tell you about the emotional side of this, because I think it's important and often overlooked. Scientists are trained to be objective, to follow the data, to set aside their personal feelings and biases. And to a large extent, that's true. But scientists are also human beings, and this crisis is taking a toll. I've talked to astronomers who have spent their entire careers studying galaxy formation, building sophisticated models, writing papers, teaching students. And now Webb is showing them that their models might be fundamentally flawed. That's hard. That's deeply, personally hard. It's not just about being wrong. Scientists are wrong all the time, and usually, it's not a big deal. You adjust your hypothesis, you run new experiments, you move forward. But this is different. This is the foundation. This is the bedrock upon which entire fields are built. If the Big Bang model needs to be seriously revised or replaced, it doesn't just affect a few papers. It affects textbooks. It affects graduate programs. It affects the careers and legacies of countless researchers. So there's resistance. Not because scientists are stubborn or close-minded, but because overturning such a fundamental theory requires extraordinary evidence and extraordinary courage. You're asking people to let go of a framework that has guided their thinking for their entire professional lives. At the same time, there's excitement. Especially among younger scientists who don't have as much invested in the old paradigm. For them, this crisis is an opportunity. A chance to be part of a revolution, to contribute to a new understanding of the cosmos. This generational dynamic is playing out in conferences, in journal papers, in late-night arguments over coffee. The old guard urging caution, the young Turks pushing for radical rethinking. It's the same pattern that plays out in every major scientific revolution. And it's messy. Science is messy. It's not the clean, orderly process you see in textbooks. It's arguments and egos and politics and funding and all the complicated human stuff that comes with any collaborative endeavor. But it's also beautiful. Because through all the mess, through all the disagreements and uncertainties, there's a shared commitment to finding the truth, to following the evidence, to building a model of reality that actually matches reality. And that's what we're doing. We're fumbling in the dark, yes. We're uncertain and confused and sometimes frustrated. But we're looking. We're questioning. We're trying. Let me bring this back to Webb for a moment, because I want to make sure you understand what an incredible achievement this telescope is, regardless of the crisis it's causing. The engineering alone is mind-boggling. Webb is basically a giant, origami telescope. It was too big to launch fully assembled, so it had to be folded up like a massive, incredibly delicate piece of cosmic origami, launched into space, and then unfolded perfectly, with no room for error. The primary mirror is made of 18 hexagonal segments, each covered in a microscopically thin layer of gold. The mirror is huge, 6.5 meters across, compared to Hubble's 2.4 meters, giving it much more light-gathering power. And it's located not in low Earth orbit like Hubble, but at a point called L2, about 1 million miles from Earth. At L2, Webb can maintain its position relative to Earth and Sun with minimal fuel, and it can keep its instruments incredibly cold, which is crucial for infrared observations. Because that's the key to Webb's power, it sees in infrared. While Hubble sees mostly visible light, the kind of light our eyes detect, Webb sees the heat signature of the universe. Why does this matter? Because of the expansion of space. Light from distant galaxies gets stretched as it travels to us, shifted toward the red end of the spectrum and beyond, into the infrared. The further away something is, the more its light is redshifted. So by observing in infrared, Webb can see things that are so far away, and therefore so far back in time, that their light has been completely shifted out of the visible range. We're literally seeing back to the dawn of the cosmos. And what we're seeing is challenging everything. But here's what I want you to understand, that's not a failure. That's actually what we hoped for, even if we didn't realize it at the time. Science doesn't progress by confirming what we already know. It progresses by discovering things we didn't expect, by being surprised, by having our assumptions challenged. If Webb had just shown us exactly what our models predicted, it would have been, well, kind of boring, actually. It would have been a technical achievement, sure, but not a revolutionary one. Instead, Webb is forcing us to rethink fundamental aspects of our cosmic story. It's pushing us to be more creative, more careful, more humble. It's reminding us that the universe doesn't care about our theories or our egos. It is what it is, and our job is to figure out what that is. So yes, there's a crisis in cosmology. Yes, our models are struggling. Yes, we might need to revise or replace some of our most cherished theories. But that's not a disaster. That's science working exactly as it should. Let me talk about what comes next, because I think that's the most exciting part of all this. Webb is still early in its mission. It's designed to operate for at least 10 years, possibly longer if everything keeps working. And every day, it's gathering more data, pushing deeper into the cosmos, finding more impossible galaxies and perplexing phenomena. Over the next few years, we're going to accumulate an enormous amount of information. Not just about distant galaxies, but about exoplanets, star formation, the structure of the early universe, the nature of dark matter and dark energy, and countless other topics. And as that data comes in, theories will be proposed, tested, refined, or discarded. We'll try early dark energy models and see if they hold up. We'll look for evidence of modified gravity and see if the patterns match. We'll search for dark stars and direct collapse black holes and all sorts of exotic possibilities. Some of these ideas will work. Some won't. But gradually, painfully, through argument and observation and analysis, we'll converge on a better understanding. Maybe not the complete truth, I doubt we'll ever have that, but a closer approximation, a more accurate model. And here's the beautiful part, we get to watch it happen. We're living through one of those rare moments in history when our fundamental understanding of reality is shifting. When the old maps are being redrawn. When everything is up for grabs. Future historians of science will look back at this decade as a pivotal moment, the time when cosmology entered a new era. And we're here for it. How cool is that? There's another aspect of this that I find fascinating, and it has to do with the philosophy of science and the limits of human knowledge. We've always known, at some level, that our scientific theories are provisional. They're the best explanations we have given the available evidence, but they're not absolute truths. Newton's laws of motion worked beautifully for centuries, until we discovered situations, very fast speeds, very strong gravitational fields, where they broke down. Then Einstein came along with relativity, which explains more but is itself almost certainly not the final word. Every generation of scientists thinks they're close to a complete understanding, and every generation is proven wrong. Not because they were stupid or lazy, but because the universe is incredibly complex, and we can only see so much with the tools we have at any given time. Webb is just the latest, most powerful tool. But it's still limited. It can only see so far, detect certain wavelengths, resolve certain details. There are things beyond its reach, phenomena it can't detect, questions it can't answer. And that's okay. That's how science works. Each new instrument opens a window, and through that window, we see things we never saw before. Often, those new views raise as many questions as they answer. And so we build better instruments, look deeper, and the cycle continues. There's a kind of humility in this that I find beautiful. We'll never know everything. We'll never have the complete picture. But we keep trying anyway, driven by curiosity and wonder and the sheer human need to understand our place in the cosmos. The crisis that Webb has created is, in a way, a gift. It's a reminder of our limitations, yes, but also of our potential. It shows that there's still so much to discover, so many mysteries left to solve. The universe is not a closed book. It's an infinite library, and we've barely begun to read it. Let me address something that I think troubles a lot of people. If our models are so wrong, does that mean all of science is unreliable? Can we trust anything scientists tell us? The answer is yes, absolutely, but with the understanding that scientific knowledge is always evolving. When we say our cosmological models might be wrong, we don't mean that everything we thought we knew is garbage. We mean that the models are incomplete or need refinement in certain areas. Most of what we know about the universe is still solid. The expansion of space is real. The cosmic microwave background is real. The light from distant galaxies is real. What's up for debate is the interpretation of these phenomena, the framework we use to understand them, the story we tell about how they all fit together. It's like discovering that your map of a city is missing a few streets. The buildings are still where you thought they were. The major landmarks are accurate. But there are some pathways you didn't know about, some connections you missed. Your map wasn't useless, it was just incomplete. That's where we are with cosmology. Our map has gotten us pretty far. It's allowed us to make predictions that have been confirmed, to understand phenomena that once seemed mysterious, to trace the history of the universe back to the earliest moments. But now we're finding features that don't fit, and we need to update the map. That's not a failure of science. That's science working exactly as intended. The same process played out with Newton and Einstein. Newtonian physics wasn't wrong in the sense of being completely false. It was and is an excellent approximation for most situations we encounter in everyday life. You can send a spacecraft to Mars using Newtonian physics and get there just fine. But when you're dealing with very strong gravity or very high speeds, you need Einstein's general relativity. Newton's laws are a special case, a useful approximation that works well under certain conditions but breaks down under others. The Big Bang model might be similar. It might be a useful approximation that works well for most of cosmic history but breaks down in the earliest moments or on the largest scales. And whatever replaces it, whether that's a big bounce model or early dark energy or modified gravity or something we haven't thought of yet, will probably include the Big Bang as a special case, just as relativity includes Newtonian physics. This is how science progresses. Not by throwing everything out and starting over, but by refining and extending our theories, by finding the boundaries where they work and where they don't, by building more comprehensive frameworks that include the old knowledge while explaining new observations. So when you hear about the crisis in cosmology, don't think of it as science failing. Think of it as science doing what it does best, confronting its limitations, questioning its assumptions, and striving for a deeper understanding. Now, let me get a bit speculative and talk about some of the more exotic possibilities that are being discussed in the wake of Webb's discoveries. One idea that's been around for a while but is getting renewed attention is the multiverse. The concept is that our universe, everything we can see and detect, is just one of many universes, each with its own laws of physics, its own constants of nature, its own history. In this view, the fine-tuning of our universe, the fact that the constants seem perfectly calibrated to allow for stars, galaxies, and life, isn't a coincidence or a sign of design. It's a selection effect. There are countless universes with different constants, and we happen to live in one of the rare ones where conditions allow for complexity and observers like us. Webb's discoveries could fit into this framework. Maybe the early universe we're seeing is so weird because we're catching glimpses of quantum fluctuations from other universes bleeding into our own. Maybe the impossible galaxies are actually from a different pocket universe with slightly different physics. This is highly speculative, of course. The multiverse is a controversial idea because it's extremely difficult, maybe impossible, to test. If other universes are truly separate from ours, causally disconnected, then we can never observe them directly. We can only infer their existence from indirect effects or theoretical arguments. But that doesn't mean the idea is without merit. Sometimes physics takes us to places that seem philosophically strange or observationally challenging. Quantum mechanics is full of bizarre phenomena that seem impossible, yet the theory works incredibly well. Black holes were once considered purely theoretical curiosities, but now we've photographed them. So maybe the multiverse is real. Maybe our universe is one bubble in an infinite foam of universes, each with its own properties. It's a dizzying thought, but not one we can rule out. Another exotic possibility involves the nature of time itself. Our models assume that time flows uniformly, that the laws of physics are the same at all times and places. But what if that's not true? Some physicists have proposed that the constants of nature, things like the strength of gravity or the mass of the electron, might actually vary over time or space. If that's the case, then the early universe might have had different physics, which would explain why it behaves differently than our models predict. This is an idea that's been tested to some extent. Astronomers have looked at the light from distant quasars, searching for tiny shifts in spectral lines that would indicate a change in physical constants. So far, the results have been negative or inconclusive. But Webb might have the sensitivity to detect such changes if they exist. If we do find evidence that the constants of nature evolve, it would be revolutionary. It would mean that the universe is even more dynamic than we thought, that the very fabric of reality is shifting over cosmic time. It would open up entirely new areas of research and raise profound questions about why the constants are what they are and how they change. Then there's the possibility of exotic matter or fields that we haven't detected yet. Not just dark matter and dark energy, but other components of the universe that interact so weakly with normal matter that we've missed them. Some theories propose the existence of axions, hypothetical particles that could make up dark matter. Others suggest hidden dimensions of space that we can't directly access. Still others involve more esoteric ideas like cosmic strings or domain walls, topological defects left over from phase transitions in the early universe. Webb might be able to find evidence for some of these ideas. For example, if cosmic strings exist, they would distort the images of distant galaxies in characteristic ways. If there are hidden dimensions, they might affect how gravity behaves on large scales. If there are exotic fields, they might leave signatures in the distribution of galaxies or the properties of the cosmic microwave background. Again, this is all speculative. We're throwing spaghetti at the wall, seeing what sticks. But that's what you do when you're in a crisis. You explore every possibility, no matter how strange, because conventional thinking has failed. And who knows? Maybe one of these wild ideas will turn out to be right. Science has a history of surprising us. Let me bring this back to Earth for a moment and talk about what all of this means for us, for humanity, for our sense of place in the cosmos. It's easy to feel small and insignificant when you're confronted with the immensity of the universe. Webb's images show us galaxies billions of light-years away, each containing hundreds of billions of stars, each star potentially hosting planets. The scale is incomprehensible. And now we're finding out that the universe might be even stranger than we thought. That it might be cyclic, eternal, one of many. That the Big Bang might not be the beginning but just a moment in an infinite sequence. It's overwhelming. It can make you feel like nothing you do matters, like we're just specks of dust in an uncaring void. But I think that's the wrong way to look at it. Yes, we're tiny. Yes, the universe is vast. But we're also the part of the universe that's aware of itself. We're the way the cosmos has become conscious, capable of wonder and curiosity and love. Every time we point a telescope at the sky, every time we take a measurement or write an equation or have a debate about the nature of reality, we're participating in something profound. We're the universe trying to understand itself. And that's not insignificant. That's miraculous. Think about the chain of events that had to happen for us to be here. A star had to explode, scattering heavy elements into space. A cloud of gas had to collapse, forming a new star and a solar system. Planets had to coalesce. One of those planets had to be at just the right distance from its star, with just the right conditions for liquid water. Chemistry had to give rise to biology. Simple life had to evolve into complex life. That complex life had to develop intelligence, consciousness, the ability to ask questions and seek answers. And here we are, wondering about the Big Bang, building telescopes that can see to the edge of the observable universe, grappling with the fundamental nature of space and time and matter. It's astonishing. And the fact that our understanding is incomplete, that we're struggling with new observations that don't fit our models, that doesn't diminish the achievement. If anything, it makes it more remarkable. Because it means we're still learning, still discovering, still pushing the boundaries of human knowledge. The crisis in cosmology isn't a setback. It's a new chapter. It's an invitation to dig deeper, think harder, imagine more boldly. And that's exciting. That's what being human is all about. Let me talk about some of the practical implications of all this, because it's not just abstract philosophizing. The questions we're grappling with have real-world consequences. For one thing, understanding the expansion rate of the universe is crucial for measuring cosmic distances. If we get the Hubble constant wrong, all our distance measurements are off, which means our estimates of the sizes and ages of galaxies are wrong, which affects everything from star formation models to theories of galaxy evolution. Getting this right matters if we want to understand our place in the cosmos, if we want to know how typical or unusual our galaxy is, if we want to predict the future evolution of the universe. And then there's dark energy. If dark energy is real and the universe is accelerating, that has profound implications for the far future. Eventually, trillions of years from now, the expansion will carry distant galaxies beyond our cosmic horizon. They'll be moving away from us so fast that their light can never reach us. The universe will become increasingly empty and dark, a cold and lonely place. But if dark energy isn't what we think it is, if the expansion is behaving differently than our models predict, then the future might be different. Maybe the acceleration will slow or stop. Maybe the universe will recollapse in a big crunch. Maybe something else entirely will happen. We don't know. And not knowing means we can't predict the ultimate fate of everything. There are also implications for the search for life beyond Earth. If galaxies formed faster than we thought, if stars and planets were around earlier, then life had more time to develop. The universe could be teeming with civilizations much older and more advanced than ours. On the other hand, if the early universe was more chaotic and violent than our models suggest, with more supernovae and more intense radiation, then conditions might have been hostile to life for longer. The emergence of life might be rarer than we hoped. Understanding the timeline of cosmic history is crucial for understanding the likelihood of life and intelligence elsewhere in the universe. And finally, there are technological spin-offs. The Webb telescope required the development of new materials, new manufacturing techniques, new data analysis algorithms. These innovations don't just stay in astronomy, they filter out into the broader economy, driving progress in everything from medical imaging to telecommunications to materials science. The crisis in cosmology is driving innovation, forcing us to develop new tools and methods, and those will have benefits far beyond astronomy. So yes, this is about fundamental questions of existence and meaning. But it's also about practical knowledge and technological advancement. It's all connected. Now, I want to address a question that I get asked a lot. If our models are wrong, does that mean scientists were lying to us? Were they making stuff up? Absolutely not. Scientists work with the best information available at the time. The Big Bang model wasn't a lie or a fantasy. It was, and is, the best explanation we have for a wide range of observations. It's been tested and refined over decades. It's made predictions that have been confirmed. But science is self-correcting. When new data comes in that doesn't fit the model, scientists adjust. They don't cling to old ideas out of stubbornness or pride. Well, most don't. They follow the evidence. What's happening now with Webb isn't scientists admitting they were wrong in a shameful way. It's scientists doing exactly what they're supposed to do, updating their understanding in light of new information. This is a strength of science, not a weakness. Religions and ideologies often resist change, defending their doctrines against all challenges. Science embraces change because the goal isn't to defend a particular worldview. The goal is to understand reality as accurately as possible. So when you hear about the crisis in cosmology, don't think of it as scientists failing. Think of it as science succeeding at its primary mission, the pursuit of truth, wherever that leads. Let me try to bring all of this together and give you a sense of where we stand right now, at this pivotal moment in the history of cosmology. We've built the most powerful telescope humanity has ever constructed. We've pointed it at the earliest epochs of the universe, expecting to confirm our theories and fill in the details of cosmic history. Instead, we've found anomalies, impossible galaxies, supermassive black holes that shouldn't exist, an expansion rate that doesn't make sense, a universe that looks far more mature and complex in its infancy than our models predict. These discoveries have thrown the field into crisis. Not a bad crisis, a productive one. A crisis that's forcing us to question our assumptions, to explore new ideas, to push the boundaries of our understanding. We don't have all the answers yet. We're not even sure we're asking the right questions. But we're working on it. Every day, new papers are published, new simulations are run, new observations are made. Slowly, painfully, we're feeling our way toward a better understanding. It might take years. It might take decades. But eventually, we'll figure it out. We'll find a model that explains Webb's observations, that resolves the Hubble tension, that makes sense of the impossible galaxies. That model might look a lot like the Big Bang with some tweaks and adjustments. Or it might be something radically different, a new paradigm that changes how we think about everything. Either way, it will be a triumph. Because every crisis in science is an opportunity. A chance to learn something new, to go deeper, to understand more. And that's what we're doing. We're standing at the edge of the known, staring into the unknown, and daring to take the next step. The universe is waiting. It has secrets to tell, if we're brave enough to listen. And I, for one, can't wait to see what we discover next. The James Webb Space Telescope has given us a gift. Not the gift of confirmation and certainty, but the gift of mystery and possibility. It's reminded us that the universe is far stranger and more wonderful than we imagined. It's reminded us that we don't have all the answers. That our models, as sophisticated as they are still just approximations. That reality is richer and more complex than our theories can capture. And that's beautiful. That's what makes science worth doing. Not the moments of certainty, but the moments of wonder. Not the times when everything makes sense, but the times when we realize how much we don't know. So yes, there's a crisis in cosmology. Yes, our models are struggling. Yes, We're uncertain about some of the most fundamental aspects of the universe. But that uncertainty is not a weakness. It's an invitation. An invitation to keep looking, keep questioning, keep exploring. Because out there, in the infrared dark, the universe is waiting to tell us its true story. And we're listening. The human side of discovery. Let me tell you something that doesn't make it into the press releases or the scientific papers. This crisis is intensely personal for the people living through it. I've talked to cosmologists who are in their 60s and 70s, who built their entire careers on the Big Bang model. They wrote the textbooks that taught the current generation. They developed the simulations that predicted what Webb would see. They were confident, not arrogantly, but reasonably confident based on decades of successful science, that we understood the broad strokes of cosmic history. And now they're watching their life's work being questioned. Not dismissed, questioned, which in some ways is harder. If someone just said, "You're wrong, here's why," you could fight back or accept it. But this ambiguity, this uncertainty, this sense that maybe we missed something fundamental, that's harder to process. I've seen the strain on their faces at conferences. The way they defend their positions, not out of stubbornness, but out of a deep belief that the framework they've spent decades building can't be that wrong. It works for so much. It explains so much. How can it fail so completely when it comes to the earliest galaxies? But I've also seen something else, excitement. Even among the old guard, there's a spark of excitement at the possibility that we're on the verge of something new. Because at the end of the day, most scientists got into this field because they wanted to understand the universe, not because they wanted to be right. And if being right means accepting that your old models were incomplete, well, that's the price of progress. The younger researchers, the grad students and postdocs, are in a different position. For them, this isn't a crisis, it's an opportunity. They're not invested in the old paradigm. They didn't spend years building models based on assumptions that are now being questioned. They're free to think outside the box, to propose radical solutions, to take risks that more established scientists might hesitate to take. And that's healthy. That's how science moves forward. The old generation pushes back, demanding rigor and evidence. The young generation pushes forward, willing to entertain ideas that seem outlandish. And somewhere in the tension between conservation and innovation, truth emerges. But there's also anxiety. Because if the field is in crisis, what does that mean for career prospects? If all the old models are being questioned, is your PhD thesis still relevant? If the textbooks need to be rewritten, does your years of study still count for something? These are real concerns. Academia is a competitive, high-pressure environment, and uncertainty about fundamental issues makes everything harder. You can't just follow the established playbook and expect success. You have to navigate uncharted waters, and that's scary. I think about the grad students working on their dissertations right now, trying to choose a topic in a field where the ground is shifting beneath their feet. Do you work on refining the old models, hoping they can be saved? Do you bet on a radical new approach, knowing it might be completely wrong? Do you hedge your bets and work on something observational that will remain valuable regardless of which theoretical framework prevails? There's no easy answer. And the stress of that uncertainty takes a toll. But here's what I want you to understand: this is still better than the alternative. A field where everything is settled, where all the big questions are answered, where we're just filling in minor details, that's a dead field. That's a field that's no longer at the frontier of human knowledge. The crisis means we're alive. We're relevant. We're grappling with real, important questions. And yes, it's uncomfortable and uncertain and sometimes frustrating. But it's also thrilling. It's why we do this. The technical details matter. Let me get into some of the nitty-gritty details, because I think they're important for understanding both the problem and the potential solutions. When we talk about the impossible galaxies, we need to be specific about what makes them impossible. It's not just that they're large or bright. It's a combination of factors that, taken together, don't fit our models. First, there's the mass. These galaxies contain somewhere between 10 billion and 100 billion solar masses worth of stars. That's comparable to the Milky Way, which is a pretty substantial galaxy by modern standards. Second, there's the age. Based on their distance and the expansion rate of the universe, we're seeing these galaxies as they were just 300 to 500 million years after the Big Bang. That's less than 4% of the current age of the universe. Third, there's the structure. These aren't just clouds of stars. They have well-defined shapes, disks, bulges, spiral arms in some cases. That kind of organization takes time to develop. Fourth, there's the chemical composition. Spectroscopic analysis shows the presence of heavy elements, carbon, oxygen, nitrogen, iron, that can only be produced in stellar nucleosynthesis. This means at least one, probably multiple generations of stars had to form, live, and die to enrich the gas to the levels we observe. Each of these factors individually is challenging but potentially explainable. It's the combination that creates the problem. Let's do the math. To form a 10 billion solar mass galaxy in 300 million years, you need to form stars at an average rate of about 30 solar masses per year. That's high but not impossible. We see starburst galaxies in the local universe forming stars at similar or higher rates. But here's the catch: you can't just form stars. You need to form them, have them evolve, have some explode as supernovae, enrich the interstellar medium with heavy elements, and then form new stars from that enriched gas. This stellar recycling takes time. A massive star lives for maybe 10 million years before exploding. A Sun-like star lives for 10 billion years, but the first ones might have been different. Even if we assume everything happens as fast as physically possible, you still need several tens of millions of years for the first cycle of star formation and enrichment. That leaves you with maybe 250 million years to build the entire galaxy, and you have to do it at an incredibly high efficiency. Essentially, every bit of available gas has to turn into stars, with minimal waste. That's very different from what we see in local galaxies, where star formation efficiency is typically only a few percent. Can it be done? Maybe. If conditions in the early universe were very different from what we see today, denser gas, less turbulence, different magnetic fields, maybe star formation was much more efficient. But this requires assumptions about early universe conditions that we can't directly verify. We're essentially inventing a story to fit the data, and while that's not necessarily wrong, it's uncomfortable. We like our theories to be predictive, not just descriptive. The black holes are an even bigger problem, mathematically speaking. A black hole grows by accreting matter, and there's a fundamental limit to how fast this can happen, set by radiation pressure from the infalling material. This is the Eddington limit I mentioned earlier. If you start with a black hole formed from a single massive star, say 100 solar masses, and you let it grow at the Eddington limit for 300 million years, you can get it up to maybe 1 million solar masses. That's already assuming continuous feeding with no breaks, which is unrealistic. But Webb is finding black holes with masses of 1 billion solar masses or more. To get there, you either need to start with much bigger seeds, thousands or tens of thousands of solar masses, or you need to exceed the Eddington limit somehow. Direct collapse black holes are one way to get bigger seeds. The idea is that under certain conditions, very pristine gas with no heavy elements, no fragmentation into smaller clumps, an entire massive cloud can collapse directly into a black hole without forming stars first. This is theoretically possible, but it requires very specific conditions that may not have been common in the early universe. And even if you start with a 10,000 solar mass seed, you still need to grow it by a factor of 100,000 to reach 1 billion solar masses, which pushes the limits of what's possible in the available time. Super Eddington accretion is another possibility. Maybe black holes can exceed the Eddington limit if the accretion flow is geometrically thick or if magnetic fields play a role in channeling the infalling matter. There's some theoretical and observational support for this, but it's not fully understood. Or maybe the black holes didn't form from stars at all. Maybe they're primordial black holes, formed in the extremely early universe from quantum fluctuations or phase transitions. These could have any mass, including very large masses, and they'd be sitting around waiting for galaxies to form around them. This is an attractive idea in some ways, because it solves multiple problems at once. Primordial black holes could also be a component of dark matter, and they provide ready-made seeds for supermassive black holes in galaxies. But primordial black holes have their own issues. We've never detected one. And various observations, from the cosmic microwave background to gravitational wave events to the distribution of matter in the universe, constrain their abundance. It's not clear there can be enough of them to explain what we're seeing. So every explanation has problems. Every solution requires assumptions or introduces new questions. That's why this is a crisis. We're not just missing a detail or two. We're missing a coherent framework that can explain everything we're observing. The Hubble tension in detail. Let me spend more time on the Hubble tension, because it's central to the crisis and it illustrates the nature of the problem beautifully. The Hubble constant is usually written as h, and it has units of velocity per distance, specifically kilometers per second per megaparsec. What this means is that for every megaparsec of distance from us, space is expanding at h kilometers per second. If h is 70, then a galaxy 1 megaparsec away is receding at 70 kilometers per second, a galaxy 2 megaparsecs away is receding at 140 kilometers per second, and so on. The relationship is linear, a direct consequence of the uniform expansion of space. Now, 70 might not sound like much. But remember, a megaparsec is about 3.26 million light-years. And there are galaxies billions of light-years away, which means they're receding at a significant fraction of the speed of light. The Hubble constant also tells us the age of the universe. If you know how fast things are moving apart now, and you assume the expansion has been roughly constant, which is an oversimplification, but bear with me, you can calculate how long ago everything was at the same point. That's the age of the universe, roughly 13.8 billion years, depending on the exact value of h and some other factors. So getting h right is important. It's not just an academic exercise. It affects our understanding of cosmic history, the ages of stars, the distances to galaxies, everything. The two main methods for measuring h are very different, which is why the disagreement is so troubling. The first method uses the cosmic microwave background. This is the radiation left over from when the universe was about 380,000 years old, the moment when it became transparent to light for the first time. Before that, the universe was so hot and dense that light couldn't travel freely. It would immediately scatter off electrons and protons. But as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen, and suddenly light could travel unimpeded. That light has been traveling through space ever since, and we can detect it today as a faint microwave signal coming from all directions. It's not perfectly uniform. There are tiny temperature fluctuations, less than 0.01%, that correspond to slight variations in density in the early universe. These fluctuations are incredibly important. They're the seeds of all this tea. Structure we see today, galaxies, clusters, superclusters. And the pattern of the fluctuations encodes information about the composition and expansion history of the universe. By analyzing this pattern in exquisite detail, which satellites like WMAP and Planck have done, we can extract all sorts of parameters, including h. The value we get is about 67 kilometers per second per MPC, with an uncertainty of less than 1%. That's remarkably precise. And it's not based on any one piece of data. It's based on fitting a comprehensive model to thousands of data points, all of which have to be explained consistently. The fact that we can do this, that the model works so well, is a testament to the power of modern cosmology. The second method uses what's called the cosmic distance ladder. It's a series of techniques, each building on the previous one, that allows us to measure distances to farther and farther objects. At the bottom of the ladder are nearby stars whose distances we can measure directly using parallax, the apparent shift in a star's position as Earth orbits the Sun. This gives us a baseline. Next are Cepheid variable stars. These are stars that pulsate with a regular period, and there's a relationship between the period of pulsation and the star's intrinsic brightness. By measuring the period, we know how bright it really is. By measuring how bright it appears, we can calculate its distance. We find Cepheids in nearby galaxies and use them to calibrate the next rung of the ladder, which might be type Ia supernovae. These are exploding stars that reach a fairly consistent peak brightness, making them excellent, standard candles for measuring distances to very distant galaxies. At each step, you're calibrating against the previous step, building up a chain of measurements that extends billions of light years out into the universe. And at the end of this chain, by measuring the distances and velocities of many galaxies, you can calculate h. The value you get is about 73 kilometers per second per MPC, with an uncertainty of a few percent. Now, 67 versus 73 might not seem like a huge difference. It's less than 10%. But in cosmology, especially with measurements this precise, it's enormous. The uncertainties don't overlap. One method says 67 with an uncertainty of about 0.5. The other says 73 with an uncertainty of about 1. These are statistically incompatible. At first, people thought it was measurement error. Maybe the Cepheid distances were off due to dust absorption or stellar crowding. Maybe the cosmic microwave background analysis was missing some systematic effect. So researchers double-checked everything. They used different techniques to measure distances. They analyzed the data different ways. They looked for sources of bias or error. And the disagreement persisted. If anything, as measurements improved, the gap got bigger. Webb was supposed to help by providing the most precise Cepheid measurements ever. And it did. It confirmed that the distance ladder measurements were right. H really is about 73 from that method. Which means the cosmic microwave background method must be wrong. Or the cosmic microwave background method is right, and the distance ladder is wrong. Or both are right, and something weird is going on with the universe. That last possibility is what has people excited and nervous. Because if both measurements are correct, it means our model of the universe, the Lambda CDM model that's been so successful, is missing something. Maybe there's a component of dark energy that was more important in the early universe. Maybe the expansion rate was different then than we thought. Maybe the curvature of space is slightly different from what we assumed. Maybe there's new physics at play. Any of these possibilities would require revisions to our cosmological model. Not small tweaks, but fundamental changes. And that's why this is called the Hubble Tension. It's not just a disagreement about a number. It's a crack in the foundation of cosmology. What comes next? So where do we go from here? What are the next steps in resolving this crisis? First, more data. Always more data. Webb is still operating, still observing, still sending back images and spectra. Every new observation is a piece of the puzzle. The more pieces we have, the clearer the picture becomes. We need to find more of these early galaxies and study them in detail. We need to measure their masses, their star formation rates, their chemical compositions. We need to understand their structure. Are they truly mature galaxies with disks and bulges, or is that an illusion created by viewing geometry? We need to study the black holes at their centers. How massive are they really? Are they actively accreting, or are they dormant? What's the relationship between the black hole mass and the galaxy properties? We need to push even deeper, looking at even earlier times. What were the first stars really like? When did they form? How did they evolve? Webb can do much of this, but it's not the only tool. Ground-based telescopes like the upcoming Extremely Large Telescope will have complementary capabilities. Radio telescopes like ALMA and the SKA can study the cold gas and dust in early galaxies. X-ray telescopes can study the black holes and hot gas. The more perspectives we have, the better we'll understand what's going on. Second, better models. We need to take the data seriously and build models that can actually explain it, not just models that fit our preconceptions. This is hard. It requires creativity and openness to new ideas. It requires being willing to question fundamental assumptions. It requires a balance between wild speculation and rigorous analysis. But it's essential. Data without theory is just a collection of facts. Theory without data is just philosophy. We need both, working together, to make progress. Third, new technologies. Sometimes the solution to a scientific problem is a better tool. Maybe we need more sensitive instruments to detect faint signals we're currently missing. Maybe we need faster computers to run more detailed simulations. Maybe we need new analysis techniques to extract more information from the data we already have. The history of astronomy is full of examples where technological advances led to theoretical breakthroughs. The telescope itself opened up the universe to human observation. Photography allowed systematic surveys. CCD cameras made precise photometry possible. Each advance brought new discoveries and new understanding. What will be the next big technological leap? Maybe space-based interferometry, allowing us to resolve details far beyond what a single telescope can achieve. Maybe quantum sensors that can detect phenomena currently invisible to us. Maybe machine learning algorithms that can find patterns in data that human analysts miss. We don't know yet, but we're working on it. Fourth, interdisciplinary collaboration. This crisis involves not just cosmology but also astrophysics, particle physics, general relativity, and even quantum mechanics. Solving it will require expertise from multiple fields. We need cosmologists to interpret the observations and build models. We need particle physicists to tell us what forms dark matter and dark energy might take. We need relativists to explore modifications to Einstein's equations. We need quantum theorists to understand the earliest moments of the universe. And we need all these people talking to each other, sharing ideas, challenging each other's assumptions. Science works best when it's collaborative, when ideas can cross-pollinate between disciplines. Finally, patience. This isn't going to be resolved quickly. Major scientific revolutions take time. The shift from geocentrism to heliocentrism took over a century. The development of quantum mechanics and relativity spanned decades. The establishment of the Big Bang model itself took half a century of work. We're in the early stages of this revolution. Webb has only been operating for a couple of years. We're still processing the data, still grappling with its implications. It will likely be years, maybe decades, before we have a new consensus model that explains everything. And that's okay. Science is a marathon, not a sprint. What matters is that we're moving in the right direction, toward a deeper understanding of reality. The broader context. Let me step back and put this crisis in a broader historical context, because I think that's illuminating. This isn't the first time astronomy has been turned upside down by new observations. In fact, it seems to happen every time we build a substantially better telescope. When Galileo first pointed a telescope at the sky in 1609, he saw things that contradicted the prevailing Aristotelian worldview. Moons orbiting Jupiter, which proved that not everything orbited Earth. Phases of Venus, which supported the Copernican heliocentric model. Mountains on the Moon, which showed that celestial bodies weren't perfect, unchanging spheres. These observations sparked a revolution that eventually overthrew centuries of accepted wisdom and established a new scientific paradigm. In the early 20th century, Edwin Hubble used the 100-inch telescope at Mount Wilson to make observations that revolutionized our understanding of the universe. He showed that spiral nebulae were actually distant galaxies, vastly expanding the known size of the universe. He discovered the relationship between distance and redshift, establishing that the universe is expanding. These discoveries laid the groundwork for the Big Bang theory and modern cosmology. In the 1990s, the Hubble Space Telescope was launched, and it too made revolutionary discoveries. It measured the expansion rate of the universe with unprecedented precision. It found evidence for dark energy by observing distant supernovae. It revealed the deep structure of distant galaxies and the evolution of cosmic structure over time. Now we have Webb, an even more powerful instrument, and once again, we're seeing things that don't fit our models. Once again, we're being forced to reconsider fundamental aspects of our understanding. This is a pattern. New tools lead to new observations, lead to new theories. The old paradigm doesn't just gracefully give way, there's always tension, always resistance, always a crisis. But eventually, a new synthesis emerges, incorporating what was right about the old view while correcting what was wrong. We're in the midst of that process now. And while it's uncomfortable and uncertain, it's also exciting. We're living through a time of intellectual upheaval, a time when the foundations of knowledge are being re-examined and rebuilt. How lucky are we to be alive for this? The role of skepticism. I want to talk about the role of skepticism in all of this, because I think it's important and often misunderstood. When scientists express caution about radical new ideas, when they demand extraordinary evidence for extraordinary claims, that's not close-mindedness. That's good science. The history of science is littered with ideas that seemed revolutionary but turned out to be wrong. Cold fusion, polywater, faster-than-light neutrinos. In each case, there was initial excitement, but careful scrutiny revealed errors in the experiments or analysis. So when someone proposes that the Big Bang is wrong, or that we need to throw out general relativity, or that we're living in a multiverse, the default response should be skepticism. Show me the evidence. Show me why this idea is better than the existing model. Show me that you've accounted for all the alternative explanations. This skepticism isn't obstruction. It's quality control. It's what separates science from pseudoscience. It's what ensures that we don't get led astray by every interesting sounding idea that comes along. But, and this is crucial, skepticism shouldn't become dogmatism. We should be skeptical, yes, but also open-minded. We should demand evidence, but also be willing to follow where the evidence leads, even if it challenges our cherished beliefs. The balance is delicate. Too much skepticism and you become resistant to change, clinging to old ideas long after they've been falsified. Too little skepticism and you become credulous, accepting every new claim without proper scrutiny. Good science requires walking that fine line. Being skeptical enough to avoid being fooled, but open-minded enough to recognize genuine breakthroughs when they occur. With the Webb crisis, I think the cosmology community is doing a pretty good job of this. There's healthy debate. People are proposing new ideas and testing them rigorously. The old models are being defended, but not dogmatically. And gradually, as the evidence accumulates, consensus is shifting. It's messy and sometimes contentious, but that's how science works. The truth emerges through argument and evidence, not through decree or authority. What this means for education. One thing that troubles me about this crisis is how it will affect education. How do we teach cosmology when the field is in flux? The traditional approach is to teach the established paradigm. You learn about the Big Bang, the cosmic microwave background, the formation of structure, the acceleration of the expansion. You learn the timeline, inflation, nucleosynthesis, recombination, dark ages, first stars, first galaxies, and so on. This is a beautiful, coherent story. It's supported by multiple lines of evidence. It's been tested extensively. It works. But it's also increasingly clear that it's incomplete. So how do we convey that to students? We can't just abandon the standard model. It's still the best framework we have, and it explains a vast amount of data. Students need to learn it to be literate in cosmology. But we also can't pretend that everything is settled. We need to teach students about the Hubble Tension, about the impossible galaxies, about the open questions and ongoing debates. We need to convey that science is a work in progress, that our understanding is always evolving, that what we teach today might need to be revised tomorrow. This is actually a great opportunity. Instead of presenting science as a fixed body of facts to be memorized, we can present it as a dynamic process of discovery. We can show students what it's like to be at the frontier of knowledge, grappling with uncertainty, trying to make sense of confusing data. That's more engaging and more authentic than just teaching the standard model as gospel. But it's also harder. It requires instructors to be comfortable with ambiguity, to say, "We don't know," when appropriate, to present multiple viewpoints and let students weigh the evidence. Not all instructors are comfortable with that. And not all students want that. Some people want clear answers, not messy debates. But I think it's important. Because the scientists of tomorrow need to be prepared for a world where fundamental questions are still open, where the paradigm might shift, where they might need to question what they've been taught. And the general public needs to understand that science is uncertain and self-correcting. That scientific consensus can change when new evidence emerges. That this is a feature, not a bug. If we can convey that, if we can use this crisis as a teaching moment, then maybe we'll raise a generation that's more scientifically literate, more comfortable with uncertainty, more able to engage with the complex issues that science presents. The cultural resonance. There's something about this crisis that resonates beyond the scientific community. The discovery that the universe is not what we thought, that our origin story might need to be rewritten, this touches on deep human concerns. We tell stories about where we came from. Every culture has creation myths, narratives about the beginning of the world and humanity's place in it. The Big Bang has become our scientific creation myth, our secular origin story. And now that story is being questioned. Not by religious fundamentalists or conspiracy theorists, but by the very scientists who helped establish it. By the data from our most advanced instruments. That's disorienting. It challenges our sense of certainty, our belief that we figured things out. But it's also exciting. It reminds us that we're still exploring, still discovering. The universe still has secrets. We haven't reached the end of knowledge. There are still frontiers to push. In a world that can sometimes feel small and fully mapped, where every corner of the earth has been explored and cataloged, where information is instantly available at our fingertips, in such a world, it's thrilling to be reminded that there are still vast unknowns. The cosmos is still strange, still mysterious, still capable of surprising us. And I think that resonates with people on a deep level. It speaks to our sense of wonder, our desire for meaning, our need to feel that we're part of something larger than ourselves. The crisis in cosmology isn't just a technical problem for specialists. It's a cultural moment, a reminder of our place in the universe and our ongoing quest to understand it. The long view. Let me close by taking the long view, because I think perspective is important. In the grand scheme of things, humans have only been doing serious astronomy for a few centuries. We've only had the Big Bang Theory for less than a century. We've only had powerful space telescopes for a few decades. We're still in the early stages of understanding the universe. We're like children who've just learned to read, puzzling over our first books, making mistakes, gradually figuring things out. The fact that our models are incomplete, that we're running into mysteries and contradictions, this isn't surprising or alarming. It's exactly what we should expect at this stage of our development. 1,000 years from now, assuming humanity survives and continues to advance, our descendants will look back at our cosmology the way we look back at medieval astronomy. They'll see how much we got wrong, how limited our perspective was, how primitive our tools were. But they'll also see that we were trying, that we were asking the right questions, even if we didn't have all the answers, that we were building the foundation for their understanding. And maybe, just maybe, they'll look back at this moment, at the crisis triggered by the James Webb Space Telescope, as a turning point. The moment when humanity began to see beyond the Big Bang, to grasp the deeper structure of reality. Or maybe not. Maybe in 1,000 years, the Big Bang will still be the dominant paradigm, with the current crisis resolved as a minor correction to the standard model. Maybe the impossible galaxies will turn out to have a simple explanation, and we'll wonder why we ever doubted. We can't know. We can only do our best with the knowledge and tools we have available today. But here's what I'm confident about: whatever the resolution, we will figure this out. Maybe not this generation, but eventually. Because that's what humans do. We observe, we question, we theorize, we test. We build models and refine them. We make mistakes and correct them. It's a slow process, sometimes frustrating, often uncertain. But it works. Over time, our understanding deepens. We get closer to truth. The James Webb Space Telescope has shown us that we're not there yet. That there's still work to do, still mysteries to solve, still questions to answer. And that's wonderful. Because a universe without mysteries would be a boring universe. A science with all the answers would be a dead science. We're alive. We're curious. We're exploring. And the universe is waiting, patient and vast, ready to reveal its secrets to those who are brave enough to look. Thank you, Webb, for reminding us of that. Thank you for the crisis, for the confusion, for the challenge. Thank you for showing us that we still have so much to learn. The adventure continues. The questions that keep me up at night. Let me be honest with you about something. There are questions related to this crisis that genuinely keep me up at night. Not because I'm a professional cosmologist, I'm not, but because I'm human, and these questions touch on things that matter to anyone who thinks about existence and meaning. The first question is this: what if we're fundamentally limited in our ability to understand the universe? Right now, we're trying to figure out what happened 13.8 billion years ago, in conditions of temperature and density that we can never reproduce. We're trying to understand phenomena, dark matter, dark energy, that we can't directly observe. We're trying to probe scales from the subatomic to the cosmic, spanning more than 40 orders of magnitude. Is it possible that some of these questions are simply beyond human comprehension? Not because we're not smart enough, but because our brains evolved to survive on the African savanna, not to understand quantum gravity or the beginning of time. There's a humbling thought for you. Maybe the universe is stranger than we can know, to paraphrase a famous quote. Maybe no matter how powerful our telescopes or how sophisticated our mathematics, we'll always be missing something fundamental because we're limited by the nature of our intelligence and our senses. I don't think that's true. I think human ingenuity is remarkable, and our track record of figuring things out is pretty impressive. But it's a possibility worth considering. The second question, what if the universe is not just one thing? What I mean is, what if the early universe operated under different physical laws than the present universe? What if the constants of nature evolve over time? What if there are multiple regions of space with different properties? If that's true, then our quest for a single, unified model of cosmology might be doomed. Because we'd be trying to fit different phenomena that have different underlying physics into one framework. This connects to the multiverse idea. If our universe is just one bubble in an infinite foam, with each bubble having different properties, then maybe the Big Bang doesn't describe the creation of everything, just the creation of our particular bubble. And maybe sometimes, we get glimpses of other bubbles. Maybe those impossible galaxies are leakage from elsewhere, cosmic contamination from a neighboring universe. Wild speculation. Absolutely. But no wilder than some of the things quantum mechanics tells us about reality. The third question, what if we're living in a simulation? I know. This sounds like science fiction. But hear me out. If it's possible to create detailed simulations of universes, and given enough computing power, it seems like it should be, then it's likely that simulated universes vastly outnumber real ones. Any sufficiently advanced civilization could run millions or billions of universe simulations. Which means, statistically, we're more likely to be living in a simulation than in the base reality. And if we are, then maybe the weird stuff Webb is finding isn't evidence of physics we don't understand. Maybe it's evidence of bugs in the code, or shortcuts taken by the programmers, or Easter eggs left for us to find. Maybe the Hubble tension exists because the simulation is running on different servers with slightly different parameters. Maybe the impossible galaxies are assets that were copy-pasted from an older version of the code. Again, wild speculation. And not particularly testable. But it's the kind of thing you start thinking about when your models of reality start breaking down. The fourth question, and this is the one that really gets me, what if this is as far as we can go? What if Webb represents the peak of human technological achievement in astronomy? What if we never build anything significantly better? What if the data we have now is all we're ever going to get? I don't think that's true. I think we'll continue to build better instruments. But it's not guaranteed. Civilizations can collapse. Technologies can be lost. Progress can stall. And if this is it, if Webb's observations represent the limit of what we can know, then we might be stuck with these mysteries forever. The Hubble tension unresolved. The impossible galaxies unexplained. The nature of dark matter and dark energy unknown. That's a sobering thought. But it's also a call to action. If our time to figure this out is limited, we'd better make the most of it. The fifth question, what does all this mean for the future of humanity? If the universe is cyclic, if we're living in one chapter of an endless book, then what happens to us in the long run? Will we survive to see the next bounce? Will we escape to another universe? Will we transcend physical form and become something we can't currently imagine? Or will we go extinct, like 99.9% of all species that have ever existed on Earth? Will we leave behind our own impossible artifacts for some future civilization to puzzle over? These are big questions. Existential questions. The kind of questions that matter more than quarterly earnings reports or political scandals or celebrity gossip. And they're the kind of questions that the web crisis forces us to confront. Because if our story of the cosmos is wrong, then our story about ourselves might be wrong too. Our place in the universe, our ultimate destiny, our meaning and purpose, all of that is tied up with our cosmological model. So yeah, these questions keep me up at night. But in a good way. In a way that reminds me that we're part of something vast and mysterious and wonderful. What we've learned so far. Let me try to summarize what we've actually learned from Webb, setting aside speculation and focusing on solid observations. 1. The early universe was more active and complex than we expected. Galaxies formed earlier, grew faster, and achieved greater mass than our models predicted. 2. Supermassive black holes existed earlier than we thought possible. This suggests either that they formed through mechanisms we don't understand, or that the early universe was conducive to rapid growth in ways we haven't accounted for. 3. The Hubble tension is real. The expansion rate measured from the cosmic microwave background doesn't match the expansion rate measured from distance ladder techniques, and the discrepancy can't be explained by measurement error. 4. The first stars might have been very different from stars today. The possibility of dark stars or other exotic objects is now being taken seriously. 5. Our current cosmological model, while successful in many ways, is incomplete or incorrect in important respects. Something is missing, and we don't yet know what it is. These are facts, or as close to facts as we get in science. They're robust conclusions based on careful analysis of high-quality data. Everything else, the Big Bounce, the multiverse, modified gravity, early dark energy, all the various hypotheses and speculations, is just that, speculation. Interesting, worth exploring, but not yet established. It's important to distinguish between what we know and what we think we know. Science is strongest when it's honest about uncertainty. The role of serendipity. One thing I haven't talked much about is the role of serendipity in scientific discovery. Sometimes, you find what you're looking for. But often, the most important discoveries are the ones you didn't expect. Webb was designed to study the first stars and galaxies. That was its primary mission. But in doing so, it stumbled onto a crisis. Nobody planned for that. Nobody predicted that the early galaxies would be so problematic. This is a pattern in the history of science. Penzias and Wilson were trying to eliminate noise from their radio antenna when they discovered the cosmic microwave background. Röntgen was working with cathode rays when he discovered X-rays. Fleming was studying bacterial cultures when he discovered penicillin. Serendipity. happy accidents, unexpected findings that turn out to be more important than the original goal. This is why we fund basic research, even when the practical applications aren't clear. You never know what you might find. You never know what seemingly esoteric discovery might lead to revolutionary applications or fundamental insights. Webb is giving us serendipity in spades. We pointed it at the early universe to confirm and refine our models, and instead, we're being forced to rethink everything. That wasn't the plan. But it might be the best possible outcome. Because confirmatory science, while important, doesn't push boundaries. It's the unexpected results, the anomalies, the things that don't fit, those are what drive progress. The global nature of this endeavor. One more thing I want to emphasize, this is a global effort. The data from Webb is being analyzed by researchers from dozens of countries. The theoretical work being done to explain the observations involves collaborations across continents. The next generation of instruments being planned are international projects. This is humanity as a species, working together to understand the universe. Not Americans or Europeans or Asians. Humans. Yes, there's competition. Yes, there are egos and nationalism and all the usual human foibles. But there's also cooperation. Data is shared. Results are peer-reviewed internationally. Conferences bring together people from all over the world to exchange ideas. In a world that often seems divided by politics and ideology, science is one of the few truly global enterprises. And cosmology, perhaps more than any other field, is inherently universal. We're studying the cosmos, which belongs to everyone and no one. The crisis Webb has triggered affects all of us equally. No country or culture is insulated from the implications. We're all in this together, trying to make sense of the universe we inhabit. That's beautiful. That's hopeful. That's a glimpse of what humanity can achieve when we work together toward common goals. The personal impact. Let me tell you how this crisis has affected me personally, because I think that's illustrative of its broader impact. I'm not a cosmologist. I'm someone who's interested in science, who tries to stay informed about major developments, who thinks about these big questions. And the Webb findings have genuinely changed how I see the world. I used to have a reasonably confident grasp of cosmic history. I knew the story: Big Bang, inflation, first stars, first galaxies, gradual evolution to the present day. It was a satisfying narrative, well supported by evidence, consistent with observations. Now, I'm not so sure. I mean, I still think something like the Big Bang happened. But the details, the timeline, the mechanisms, all of that is up for grabs. And that uncertainty extends beyond cosmology. If we can be so wrong about something so fundamental, what else might we be wrong about? What other scientific facts are actually just provisional best guesses? It's made me more humble. More willing to say, I don't know. More skeptical of confident pronouncements, whether from scientists or anyone else. But it's also made me more curious. If there's this much we don't understand about the universe, if there are still these huge mysteries waiting to be solved, then we're living in an incredibly exciting time. There's still so much to discover. And it's made me more philosophical. Questions about the nature of time, the meaning of existence, our place in the cosmos, these aren't just abstract puzzles. They're intimately connected to how we understand ourselves and our lives. If the universe is cyclic, if we're part of an eternal dance of creation and destruction, then maybe nothing truly ends. Maybe everything is recycled, reborn, given another chance. If we're living in a multiverse, if our universe is just one among countless others, then maybe every possibility is realized somewhere. Maybe every choice we don't make is made by another version of us in another universe. These are comforting thoughts, in a way. They suggest that existence is richer and more complex than our limited perspective allows. They hint at meanings and connections beyond what we can directly perceive. Or maybe not. Maybe the universe is cold and mechanical and indifferent. Maybe we're alone, maybe our existence is a fleeting accident, maybe there's no grand plan or ultimate purpose. I don't know. Nobody knows. But the Webb crisis has made me think about these questions more deeply, and I'm grateful for that. Looking forward. So what happens now? Where does cosmology go from here? In the short term, more observations. Webb will continue its mission, gathering data, pushing deeper into the early universe. Other instruments will contribute their own observations. Slowly, the picture will become clearer. In the medium term, new theories. Researchers are already working on models that can explain the impossible galaxies and the Hubble tension. Some of these models will fail to match new data and will be discarded. Others will survive and evolve. Eventually, a consensus will emerge. In the long term, new instruments. Webb is incredible, but it's not the end of the line. Plans are already being made for next-generation telescopes that will be even more powerful. Space-based interferometers that can resolve details far beyond what any single telescope can achieve. New detectors that can see into wavelengths currently inaccessible. Maybe even telescopes on the Moon or at the Sun-Earth L2 point that can observe without any atmospheric interference. Each new instrument will bring new data, new insights, new questions. The cycle of discovery will continue. And eventually, maybe in our lifetimes, maybe not, we'll have a new cosmological model that explains everything. A model that accounts for the impossible galaxies and the Hubble tension and all the other anomalies. A model that's as well tested and widely accepted as the Big Bang is today. That model might look a lot like the Big Bang with some modifications. Or it might be radically different, a complete reimagining of cosmic history. Either way, it will be closer to the truth than what we have now. And that's progress. But here's the thing, that new model won't be the end. It will just be another step in an endless journey. Because the universe is infinitely complex, and we'll never understand it completely. There will always be new frontiers, new mysteries, new questions. And that's as it should be. A universe fully understood would be a universe fully domesticated, stripped of wonder and mystery. Who would want that? The meaning of it all. Let me end with some thoughts on meaning, because I think that's what this is really about. Why do we care about the age of the universe, or the formation of galaxies, or the nature of dark energy? Why do we spend billions of dollars building telescopes to study things so far away and so long ago? Part of it is practical. Understanding the universe helps us understand our place in it, which can have practical implications for things like resource management and long-term survival. Part of it is intellectual. We're curious creatures. We want to know how things work. It's in our nature to explore and discover. But I think there's something deeper. I think we're searching for meaning. Not meaning in the sense of purpose, though that too, but meaning in the sense of coherence. We want the universe to make sense. We want to fit the pieces together into a comprehensible whole. The Big Bang gave us that. It gave us a narrative, a story we could tell ourselves about where we came from and how we got here. It gave us a framework for understanding our observations and making predictions. And now that framework is under stress. The story is unraveling, or at least fraying at the edges. And that's disorienting. But maybe that's the real lesson here. Maybe the universe doesn't owe us a simple story. Maybe reality is messy and complicated and doesn't fit neatly into our categories. Maybe the search for meaning isn't about finding the right answer, but about asking the right questions. About being humble enough to admit when we're wrong. About being brave enough to keep looking, even when we don't like what we find. The Webb crisis is challenging us to be better thinkers, better scientists, better humans. It's asking us to let go of our certainties and embrace uncertainty. To acknowledge our limitations while refusing to accept defeat. That's hard. Really hard. But it's also what makes us human. Our ability to question, to wonder, to seek understanding even in the face of mystery, that's what separates us from everything else we know of in the universe. So yes, there's a crisis in cosmology. Our models are breaking. Our certainties are crumbling. We're confused and uncertain and sometimes frustrated. But we're also alive. We're curious. We're engaged with reality in all its strange complexity. And that, I think, is meaningful. Not because it gives us answers, but because it connects us to something larger than ourselves. To the grand project of human knowledge. To the ongoing quest to understand the cosmos. The James Webb Space Telescope has given us many things. Beautiful images. Precise data. Revolutionary observations. But perhaps its greatest gift is this, the reminder that we don't have it all figured out. That the universe is still capable of surprising us. That there are still frontiers to explore, still mysteries to solve, still wonders to discover. In an age of instant information and algorithmic certainty, that's a precious gift indeed. So thank you, Webb. Thank you for the crisis. Thank you for the challenge. Thank you for reminding us that the universe is stranger and more wonderful than we dared to imagine. And thank you for showing us that the adventure, the great human adventure of understanding our place in the cosmos, is far from over. In fact, in many ways, it's only just beginning. The road ahead. As I finish writing this, new papers are being published, new observations are being made, new theories are being proposed. The field is in flux, dynamic, alive. Some of what I've written here will be outdated in months or years. New data will come in, supporting some ideas and contradicting others. The consensus will shift, evolve, adapt. That's the nature of science. It's always a work in progress, always provisional, always subject to revision in light of new evidence. But some things won't change. The wonder will remain. The curiosity will remain. The human drive to understand will remain. And the questions, those deep, fundamental questions about existence and origin and meaning, those will remain too. They might take different forms as our knowledge advances, but they'll always be there, pulling us forward, driving us to look deeper and think harder. So to everyone working on these problems, everyone analyzing Webb data, everyone proposing new theories, everyone building the next generation of instruments, thank you. You're doing the most human of activities, trying to understand the universe that birthed us. To everyone who's simply curious, everyone who reads about these discoveries and thinks about these questions, thank you too. Your curiosity matters. Your wonder matters. You're part of this grand endeavor, this species-wide project of understanding. And to the universe itself, in all its mysterious, beautiful, frustrating complexity, thank you for the challenge. Thank you for being just comprehensible enough to tantalize us, and just strange enough to humble us. We're watching. We're learning. We're trying. And we won't stop. Not as long as there are stars to observe and questions to ask and mysteries to solve. The crisis in cosmology isn't an ending. It's a beginning. The next chapter of our cosmic story is being written right now. And it's going to be incredible.